Mild American mustard is a colloidal system primarily composed of finely dispersed mustard seed particles suspended in a water-based matrix. It also contains sugar, spices, and thickening agents which contribute to the mustard's texture, stability, and overall quality.
The water and vinegar components are responsible for the hydration and dissolution of the hydrocolloid particles. To start with, water solubilizes xanthan gum and starches due to them containing many hydroxyl groups, which enables them to form hydrogen bonds with the water. The water molecules enter the starch granules to form hydrogen bonds with hydroxyl groups, replacing the original intramolecular hydrogen bonds, which destroys the starch granule. On the other hand, acetic acid molecules from the vinegar dissociate in the water and lower the pH of the solution. This affects the mustard mucilage as it contains hydroxyl functional groups due to the presence of galactonic acid and other acids. In acidic mediums, several hydroxyl groups found in polysaccharides undergo protonation as the pair of electrons on the oxygen atom makes it act as a base. This results in the hydroxyl groups accepting positively charged protons, enabling the mucilage to form hydrogen bonds and electrostatic interactions with water. This causes the solubilization and stabilization of the mucilage. Therefore, vinegar provides an environment where emulsification can occur more effectively.
The main flavor component of yellow American mustard is ground mustard seed. This contributes to the structure of the sauce. The high concentrations of suspended particles attract water molecules due to the H2O's strong polarity and synergistically acts with the thickened liquid phase to create a thick and pipeable sauce, a complex fluid. This is further compounded by the swelling of the mustard seed particles as they're immersed in a liquid, increasing their size and increasing the mustard powder volume fraction of the sauce. Onion and garlic powder and other spices are dehydrated and ground forms of their respective plants. When immersed in the moisture of the mustard sauce, the onion and garlic powders swell similarly to the ground mustard, enlarging and increasing the viscosity and stability of the sauce by trapping the liquid phase. Mustard seed mucilage is a soluble polysaccharide found in the seed bran with strong thickening properties and a water-soluble hydrocolloid with polar functional groups, which creates a weak gel network in a water-based medium. The mucilage is composed of water-soluble and insoluble fractions. At high concentrations, the water-soluble chains become entangled and their polar functional groups attract water molecules, thus restricting water movement and increasing the viscosity of the liquid phase.
The presence of numerous hydroxyl groups and sugar molecules dispersed throughout the mustard make it highly hydrophilic. This facilitates the dissolution of water due to hydrogen bonding of the hydroxyl groups with water molecules. When sugar is added to water, the hydroxyl groups on the sugar molecules interact with water molecules to form hydration layers around the sugar. This helps in dispersing and evenly suspending the sugar throughout the water, creating a more stable colloidal solution within the mustard, and thus a more homogeneous solution. Sugar also increases the viscosity of the mustard by disrupting the movement of water molecules, contributing to a smoother texture and mouthfeel for the mustard.
In the mustard, modified tapioca starch, mustard seed mucilage, and xanthan gum act as hydrocolloids which are used to thicken aqueous dispersions as well as increase stability and emulsifying nature of the system by forming gels. Modified tapioca starch consists of the hydrophilic glucose-based polysaccharides which self-assemble into partially crystalline granules due to physical cross-linking. This happens through intermolecular forces including hydrogen bonding, van der Waals forces, and electrostatic interactions because of the presence of hydroxyl groups on the outer side of the chains. Each semicrystalline granule has a lamellar structure of alternating crystalline and amorphous layers. In aqueous solution, the hydrogen bonding between chains break and reform with the water molecules, allowing for increased starch granule separation and therefore solubility in water. Hence, a gel network of swollen starch granules is consistently dispersed throughout the system as a colloidal suspension, which increases the water surface tension due to the intermolecular adhesion of the starch. This allows for overall thickening and stabilization of the mustard. Additionally, salt has the ability to enhance the hydration of starch molecules and promote gelatinization through strong electrostatic interactions and increase of binding free energy, therefore accelerating the gelatinization of the starch granule.
Xanthan gum is an anionic polysaccharide with a high molecular weight and good water solubility. This molecule is composed of repeating units of glucose, mannose, and glucuronic acid. Due to its anionic charge and the presence of many side chains along its structure, xanthan gum has the ability to interact with other polymers well via non-covalent bonding and physical wrapping of side chains around the backbone of adjacent polymers. This interaction contributes to the high thermal stability and viscosity of xanthan gum in dilute solutions. Additionally, the presence of hydroxyl groups along the polymer chain can form hydrogen bonds with water, making water a good solvent for xanthan gum with this particular pH, temperature, and concentration of salt.
Shapes in the dark, trying to save